There are many shapes of rocket noses. In military application, we consider them as modified ogives. The shape of the nose section may be defined by the next figure. In the vertical axis are the shapes of 9 types of noses. Meanwhile, in the horizontal axis is located the operational Mach number of the missile. As we can see, there are numbers located in the types of shapes pairing with the Mach number. The number 1 means that is the best option for this regime of Mach. The number 2 is better than number 3 but worse than number 1. And the number 3 is good. In the case of the cone and ogive, it is not recommended their use in these regimes of Mach when the radio of length and diameter is equal to 3. The 9 types of shapes cones is listed as follows: the Power Series, the Parabolic Series, the Haack Series, which includes the von Karman curve. These shapes are mathematically derived for the purpose of minimizing drag. Also, these include the popular cone and ogive noses. In this nose cone shape figure, L is the overall length of the nose cone. R is the radius of the base of the nose cone. Y is the radius at any point X, as X varies from 0 up to tip of the nose cone, to L. For the calculation of the conic shape of the rocket nose, we use the next expression. Y equals the radio between X and L multiplied by R. And to calculate the half angle, we use the next expression, and based on this half angle, we can calculate the radius at any point of X. For the calculation of the ogive shape of the rocket nose, first, we must calculate the radius of the circle that forms the ogive, called the ogive radius, lowercase r. After that, without any problem, we use the next equation to calculate the radius at any point of X. For the calculation of the Haack shape of the rocket nose, we must consider the constant K1. The range of K1 goes to 0 up to 1. If K1 goes to 0, the next equation, which we use it to calculate the shape contour, acquires the form of equation of von Karman. If K1 goes to 1/3, the same equation acquires the form of LB Haack. And if K1 goes to 2/3, the equation acquires the form of equation of tangent ogive, which we saw it before. For the calculation of the parabolic shape of the rocket nose, we must consider the constant K2. The range of K2 goes to 0 up to 1. If K2 goes to 0, the next equation, which we use it to calculate the shape contour, acquires the form of equation of conic nose, saw it before. If K2 goes to 1/2, the same equation acquires the form of half type. If K2 goes to 2/3, the equation acquires the form of equation of 3/4. And if K2 goes to 1, the equation acquires the form of equation of full parabol. For the calculation of the Power Series shape of the rocket nose, we must consider the constant lowercase k. The range of the lowercase k goes to 0 up to 1. If k goes to 0, the next equation, which we use it to calculate the shape contour, acquires the form of equation of cylinder. If k goes to 1/2, the same equation acquires the form of half type. If k goes 2/3, the equation acquires the form of equation of 3/4. And if lowercase k goes to 1, the equation acquires the form of equation of conic nose. Saw it before. In conclusion, if we return to the first figure, we can see the types of shapes we can use for a rocket design related to the velocity performance of the missile and which one is recommended to use in different cases. This figure was taken from the book Missile Configuration Design by S.S. Chin. Thank you very much for your attention. I am Pablo Arispe, and don't forget to subscribe to this channel.